Hello, a great welcome to this series on Plaxis. Myself Jarajan P. This is tutorial number 5 and it will explain how to obtain the contact stress distribution below the foundations because we know that the distribution of the contact stresses below any foundation is largely governed by the stiffness of foundations as well as the soil type. So let me take you first to the problem statement. So in order to explain the computation of the contact pressure distribution, we consider a strip footing. As you can see that the width of the strip footing is 2 meters and we consider only 1 meter length of the footing that is good enough for us. And as you can see that the strip footing is supported on a clay layer of 8 meter deep. And in order to refine the mesh in and around the strip footing, we consider a mesh refinement zone that is 1 meter away from the footing edges and also 3 meter deep. And basically the objective of this tutorial will be to compute the distribution of contact stresses below this strip foundation for a permissible settlement of 50 mm and also to obtain the average stress computed by Plaxis at this level. So for the Plaxis analysis, we consider a soil domain of size 60 meter by 1 meter. The soil parameter will be basically a Moore-Coulomb material model. The drainage type will be the drained. The unit weights used will be 18 and 16 for the saturated and unsaturated conditions. The stiffness parameters include a Young's modulus E of 4000 kN per meter square and a Poisson's ratio of 0.25. Regarding the strength parameters, the coefficient will be used as 12 kN per meter square with a friction angle phi of 24 degrees and a dilatancy angle of 0 degrees. So let us start the Plaxis analysis. Okay, fine. So let us first start with the title. We'll just fill it as a strip footing. Strip footing. Now let us fill the model boundaries. So here the model is of length 16 meters and with an x minimum of minus 8 and with an x max of plus 8, and then the model has got a length of 1 meter in the y direction. So accordingly your y minimum and y max will be minus 0.5, and then we have it as a plus 0.5. This means that we have defined the model boundaries. So this is okay for us. Now let us straight away proceed for defining the soil stratigraphy, which is done through the borehole. So let us just zoom this origin. So this is my borehole. I'll place the borehole at the origin 0, 0. So let us start defining this soil layer. We know that the tutorial consists of only a single layer, and let us start defining the limits. So we just add the soil layer, and we know that the layer is of total height or depth it is equal to 8 meters. So the bottom will keep it as a minus 8. And in this tutorial, we will not consider any water table on the top, rather we will consider at the bottom. So we'll take it as minus 8.0. Okay, so as you can see that yes, it is at minus 8 meters. So this is all regarding the definition of the soil stratigraphy. Now let us straight away proceed for defining the material. We'll press this materials button, define the new material under the set type soil interfaces. So type new, and here let us type just my clay material for identification, and the material model will be the Moore-Coulomb. We consider a drained analysis, and the unit weights in the unsaturated will take it as 16 and in the saturated condition will take it as 18. Now coming to the various important stiffness and strength parameters, we'll consider a stiffness of 4000 kN per meter square and with a Poisson's ratio of 0.25. Then we shall consider a coefficient intercept, that is a C of 12 kN per meter square with a phi value of 24 degrees and a associated dilatancy angle of 0. So this means that we have completed the definition of the soil parameters both in terms of the strength as well as the stiffness. So that is complete. Now let us just as usual assign this clay material to the borehole. So we just drag and drop. So that is okay for us. So this means that we have created the required model and we have assigned the required material, that's a sand properties to this PLAXIS model. Now this means that we can now straight away go to the next mode, that is a structures mode. So press the structures mode, and in this case we are not going to model the footing through the plate elements. Rather we will just create a surface, rectangular surface of 2 meters by 1 meters, and then we impose the required displacement of 50 mm directly on it. So let us start defining this footing surface. So before that, just zoom this area. So we'll straight away go to this create surface, okay? Or there is directly also, rather than surface, what we can do is that we can directly go for the create prescribed displacement. That's good enough for us, okay? So we'll just go on adding clicking some point. We'll define these points later. Okay, 4 points are defined. Now let us define the coordinates. So this is -1, this minus 0.5. Remember, the surface is at the top of the soil layer. Accordingly, our Z will be 0 for all the points. So -1, it is -1 minus 0.5, and the next point it will be -1 -1 0.5 0.5, and then the third point it will be 1.5, it will be 1.5, and then the final point will be 1 minus 0.5, 1 minus 0.5, minus 0.5. So this is okay for us. So as you can see that yes, we have generated a rectangular surface. This is okay for us. So as you can see that we have generated a surface prescribed displacement, and on the left side if you see, you will find that PLAXIS by default has created a unit displacement, that is a 1 meter displacement in the downward direction. So this will change it to minus of 0.05, implying that we have imposed a downward deformation or a displacement of 50 mm. So this means that we have created the surface with a prescribed displacement of 50 mm. Now, as I already mentioned earlier, we need to create a mesh refinement zone, and for mesh refinement zone we need to construct a vertical surface at 1 meter from the edge. So let us proceed for that, and this can be easily done by through the creating the surface. So we'll just, as usual, we'll create okay, yes, this is okay and this is okay, fine. So now let us start defining this particular surface, and regarding this surface, okay, let us start filling this coordinates. So this will be -2, the first coordinate will be -2 is okay for us, and then we have it as a -0.5, -0.5, and then my z value will be 0, and the next one will be -2 again. It's okay, and then we have it as a +0.5, +0.5, and z will be 0, and then let us have it as a -2. We'll have it as a -2, -2, because all my x value will be -2 only. This will be 0.5, and my z will be -3, -3. Okay, and then finally we'll have it as the last coordinate, that is a -2, -2, and then we have it as -0.5, -0.5, and then we have it as a -3, -3. So you can see that yes, one surface is already created to us. Is okay for us. Now we would like to create a copy of this surface. Okay, that means I want to place a similar surface at 1 meter on the right edge of the strip footing. So we can make use of this create array. So here we want to displace it in the x direction, 1D in x direction. The number of columns would be 2, and the required spacing we want to keep it at 1 plus 2 plus 1, that's equal to 4 meters. Okay, 4 meters. Okay, so you can say that yes, we have created another surface here on the right side of this footing. Now in order to complete this mesh refinement zone, we need to define a bottom surface as well. So let's proceed for creating the bottom surface. Okay, so let us just click for points. Okay, fine. So let us start editing these corners. So this will be -2, and then we have it as a minus 0.5, minus 0.5, and then we have it as a minus 2.5, minus 2.5. Then we have it as a 2 plus 0.5, 2 plus 0.5, and then finally 2 minus 0.5, 2 minus 0.5, minus 0.5, and we want all this is coordinate to be at a z equal to -3, so change it to -3 for every nodes. So it's -3, -3, and then -3. So okay, fine, we find that okay, the surface is exactly what we wanted, so this is okay. So means that the mesh, the definition of the mesh refinement zone is complete. Now having completely defined the soil and the structures mode, now we are ready to step on to the mesh mode. So let us start defining first of all the local refinement required for the meshes. So first we'll proceed to the footing. So select the footing. As you can see that currently it has got a fineness factor of only 0.5. So if you want to refine it further to say 0.125, so you can press this refine mesh button and just go on clicking it till the value is 0.125. So you can see that yes, currently the surface that represents the footing is meshed to a fineness factor of 0.125. Now we shall proceed for selecting that refinement is on. So we just click, you can see that this is the refinement zone that we have defined. And if you want to define this fineness factor as a 0.5, right now it is at 1. So let us just refine it as usual. So define mesh. So you can just press it till it is 0.5. Right now it is a 0.5 factor that is acceptable to us. So this means that we have defined the local refineness factor required for the footing surface as well as for the mesh refinement zone. So now we can straight away proceed for generating the mesh. So the element distribution will be taken as a medium. So this is okay. And so as you can see that the meshing is in progress. We can have a view of the mesh before proceeding to the staged construction. And it is very important that the size of the mesh required need to be fixed based on the accuracy level required and also based on the time required for the calculation. So let us see the type of the meshing that we are having for the foundation surface as well as for the refinement zone. So this means that the meshing is completed. Let us just view it, view the mesh. So you can see that yes, this is the mesh that we have just developed. You can just zoom it and see. So as you can see that yes, the foundation surface, it is meshed with a very small size elements, and right below also we have got a smaller elements compared to the mesh size outside the refinement zone. So this is acceptable to us. So this means we can straight away proceed to the staged construction. So this is a very simple problem. We don't have much problem here. So the staged construction, as usual, we have got an initial phase. We just press the initial phase, and we are using the Kaiser procedure for the calculation of the effective stresses. And all other factors will keep as default. We don't want to make any changes. And remember that in this initial phase, only the soil will be active and no surface displacements will be active. So let us proceed for creating the preserved displacement, add another phase. So just double click it. You can say that, for example, ID, you can say that this is a prescribed displacement, that is the ID for this. And we would like to start it straight away from the initial phase, and the calculation type will be plastic. And all the deformation control parameters and the numerical control parameters will be kept as it is, because that must be good enough for our problem. So this is okay for us. And now please remember that under phase 1 we need to activate the surface displacements as well. So, okay, that is we apply a displacement of 50 mm. So this means that we have completed all the modes and we are ready to step on to the calculation module. Now before calculating, I would like to select one point that is at the origin for monitoring the load versus displacement curve. So I will select one point, and at this point I will choose it as a 0 0. So as you can see that this is already 0 0, so search closest, and we have a pointer right there. So just select it. So that must be good enough for us. So that means the point is also selected. Now we are ready for performing the calculations. So just calculate, the press calculate button. You will find that yes, the calculation of the two phases are in progress. You can see the details over here. Okay, our calculations are complete. Let us start reviewing the results. So as usual, let us start from the initial phase. We would like to inspect the total stresses sigma set. So as you can see that yes, the calculated stress, it is equal to a maximum that is equal to 128 kN per meter square, which obviously exactly matches with your calculated value that is equal to gamma into h, that is equal to 16 into 8, 128 kN per meter square. So having done that, let us go to the next phase, that is the prescribed displacement phase. In the phase 1, first of all, I would like to see the variation of the displacement contours. So let us go to the phase displacement. So PUZ. So you can see that yes, this is how the displacement changes. As you know, the maximum prescribed displacement is 50 mm as indicated here, and this is how the displacement contours change along the depth of the soil profile. Now let us proceed for obtaining the load displacement profile. As you can see that the displacement applied is very small, that's 50 mm. So we expect the soil to be approximately linear in this case. So let us just visualize it, how the load displacement looks like for this settlement of 50 mm. So go straight to the course manager. The course manager, the curve points we have selected is A, that's essentially the origin of this footing. So charts, we can go straight away new, and let's select in the project the force. Will select it as Z, that's applied force, and the y-axis will select the point, and we would like to see the total displacements as I use it. So let us just okay. So fine. So let us just exchange the axis. So I would like to exchange the axis, flip the horizontal and the flip vertical. This is okay. So as you can see that yes, it passes through the origin, the curve passes through the origin, and so you can see that as the displacement is very small, 50 mm, it's almost a linear curve, P delta curve. And please remember, along the x-axis we have got the displacement, and along the y-axis the applied Fz load, and this means that corresponding to an applied load of applied prescribed displacement of 50 mm, the corresponding load is I can just proceed and see over here, and this point is 143.26 kilonewton, which is converted into a stress of 143.26 divided by the area, that's 2 into 1, that's approximately 71.5 kilonewton per meter square. This means that the mean stress calculated by PLAXIS below the cross section at a prescribed displacement of 50 mm is almost 71.6 kilonewton per meter square. So that's good enough for us. So I don't want to change this, I don't want to save this one. Okay, so now what I want to do is I want to calculate the actual contact stress distribution below the footing at a prescribed displacement of 50 mm. So what we can do is that we straightway go for, as usual, stresses. We go for the Cartesian stresses, sigma z. Okay, fine. So this is how the stresses varies. So I would like to take a plane, horizontal plane, for example, like I want to vary from minus a ton to my plus 10. So this is okay for me. So this means that right now I have got a cross section, okay, which is taken through the CG of this footing. So now what I would do is I want to zoom it a little bit. So before that, let us do one thing. Let us just reset all of this and rotate this. So this is okay for me. Okay, now let me just zoom this, because what we want is we want the deformation just below this. So from this, as you can see that the stresses below the footing are very large. very near to the edges, right? Whereas at the midpoint, we can see that in the mid zone, we can see that the stresses are almost constant. So let us just take a simple cross section in order to inspect the results. That will be very interesting for us. We'll just inspect the results. Okay, so fine. So this is how the stresses vary. Let us just zoom it. So this is very beautiful. You can see that as expected, because we have applied a prescribed displacement of 50 mm, which indicates that we have simulated a rigid footing. And in the case of a rigid footing, obviously we know that the stresses should be uniform in the mid region as shown here, and the contact stresses theoretically has to be infinite at the edges. But here we are having some finite values. Now what we can do is that we can straightaway see the variation of this contact stresses through the curves. We can go to the tools also. So we can go straight to the cross-section curves. Okay, we are interested in the prescribed displacement. This is okay. So look here. So this is very clear. You can see that this is how the stresses vary. So means that near the edges, look here, we are having almost 140 kilometer per meter square, whereas at the edges, whereas at the center we are having only 50 kilometer per meter square, which means that the average stress that is calculated by PLAXIS corresponding to a settlement of 50 mm, which we have already seen 71.2 kilometer per meter square. It is lying somewhere here. Okay, this is the mean stress because it is higher than the stresses calculated the midzone, and is also very much less than the localized maxima of the contact stresses at the edge of 140 kilometer per meter square. And all these findings are finally imported into my Excel file. That will be very easy for you to look here. This is how the so look here. This is my P delta. That's the stress versus the displacement. You can see that corresponding to 50 mm, it is 71.6 kN per meter square. And this is how the contact stress distribution changes. As you can see that at the edges it is almost 145 kN per meter square, and at the mid portion it is 50 kN per meter square, and that is calculated by the PLAXIS, that is 71.6 kN per meter square, which we have taken from this load displacement curve. It is somewhere here. So it means that the PLAXIS calculates as a mean average stress, okay, across the length of the footing. So this is very important thing. That means we need to know that whatever localized maxima that is reported under this kind of a prescribed displacement loading, it is very large at the edges, and you will find that in the mid portion you are having almost a constant value. But the observation is that the mean value that is calculated by the PLAXIS is somewhere very near to the what we call as the value very observed near the mid zone, and it is very much less than the localized maxima that is reported near the edges. So that's all regarding this tutorial. Thank you very much.